All brain cells communicate with each other by passing tiny little electrical currents. Those electrical currents generate magnetic fields, and those fields exist outside the head. So in MEG, what we try to do is measure the magnetic fields that occur outside the head, that are generated by currents in your brain. And by measuring those magnetic fields, we can then infer what your brain is doing at any one time. So there are three main limitations of the current generation of technology. One is that the signals that we measure are very low. Two, you have to keep incredibly still whilst you're being scanned. And three, it doesn't really work for children. The quantum sensors that we're working with, they're very light, and their external surface is at room temperature. So unlike the traditional sensors which have to be cryo-cooled, these things can be mounted directly onto the scalp surface. So we can bring them into much closer proximity to the brain. That increases the amount of signal that we get, increased signal to noise, therefore greater sensitivity. They're also very light, which means that we can put them on the scalp surface, and the subjects who are being scanned can move their head around whilst they're being scanned, so they don't have to keep still anymore. So that opens up lots of new avenues, in particular scanning patients who find it hard to keep still, or scanning children. Now, the other advantage for scanning children, of course, is it's no longer a one-size-fits-all helmet. Instead, we can build a bespoke helmet to fit anyone. So we could have a 2-year-old, 3-year-old, 4-year-old, and we can get the same sensitivity as we would do for an adult. So we can get a full three-dimensional picture of what the magnetic field looks like outside somebody's head. Once we've measured that magnetic field, then we can use that to infer what the currents were in the brain that were generating those magnetic fields. So we can work out exactly what the brain electrophysiology is that's supporting ongoing cognition, ongoing control in our subjects.
The main UCL interest in this project is it gives us a new kind of brain scanner that allows us to study things that we've never been able to study before, and people who have never been able to be scanned in a neuroimaging environment before. Different patient groups like children, for example. We're right opposite the National Hospital for Neurosurgery, and we're right next to Great Ormond Street Hospital. And the patients we hope to recruit from these centres are suffering with epilepsy. And what we think these sensors will do, they'll help the surgeons better target where they operate and speed up the process also, so they remove the need for some unnecessary operations and result in earlier treatments and earlier diagnosis.